speaker, Genetic Science of Information, Professor Shun-Ichi Amari. So Professor Shun-Ichi Amari has made numerous achievements in mathematical neurosciences, and he's one of the pioneers of information geometry. And today it's our great honor to have a survey of information geometry and its applications. Thank you.
Thank you for a very good introduction. And as the last speaker of the day, I know you are very tired. I'm just looking forward to wonderful dinner. Before the dinner, my talk should be not so difficult. Very easy to understand and still interesting and useful or something. It's very difficult to me, but anyway, I will try. So, my talk, I'm thinking about, I begin with a short history on information geometry from my point of view. And also, the focus is something dual geometry, Riemannian geometry with dual connection. And in particular, the dually flat manifold is very important to study. And this is because a non-flat dual connection manifold in most cases is a submanifold, dually flat manifold. Okay? And also, all the space of all the discrete probability distribution is dually flat. That implies all the discrete probability distribution is submanifold of dually flat manifold. How about function space? It's a very difficult question. Okay? And Pistone will talk about that tomorrow. But most property of dually flat structure also can be very good mathematician like Pistone will do. I cannot do. So the dual geometry, and in particular, I focus on flatness, flat manifold, that is Hessian, and also invariance criteria. And also, I would like to talk about many applications, but maybe time is limited. So if I have a time, I will talk a little bit about the various applications. Okay, so going back to the manifold of probability distribution. Okay, so we believe C.R. Rao in 1945 seminal paper, he proved Cramer-Rao theorem. Okay, and also he studied the Fisher information matrix can be give Riemannian structure to the manifold probability distribution. Everything started from that point. However, Mansell Frank-Nielsen sent me an email, shocking news. In 1929, Harold Hotel, American statistician or mathematician, not published, but as the American Statistics Annual Conference, he presented a paper. In that one, he mentioned that the Fisher information matrix is a Riemannian matrix of the manifold, and also he pointed out, say, the location scalar statistical method. It has a constant curvature. It's a big surprise, but those wonderful findings are almost unknown. Okay? We didn't know. So, but anyway, Rao did a great thing. Okay? That is a big picture paper in 1945, and I wanted to read it. Okay, I searched in Japan. My university, University of Tokyo is the biggest university, but they don't have. 1945 is the end of the war. And also, journal is Calcutta Journal of Mathematics, very local journal. At that time, Rao was 24, a very young guy. Okay. But anyway, later I met Rao. He promised me, oh, I will send you one copy. He didn't, he forgot. But I got that from another guy, and it's very interesting. But anyway, then the Chenzo, Russian mathematician, he's a student. He was a student of Columbia. Okay? And he did something the following after Rao's idea. Why Fisher information matrix? Is there any other Riemannian matrix reasonable? And he introduced the concept of invariance. Okay. And he proved that the Fisher information matrix is a unique Riemannian matrix from the point of view of invariance. And he also extended that concept to affine connections. Okay. And then later, Bradley F. Chenzo, his book was in Russian. Okay. So it's very difficult to read. However, when I published my first paper, I submitted to the analysis of statistics. And of course, I didn't know about F. But some reviewer pointed out there was a Russian work in Chenzo, and your idea is very close to his idea. And later, the reviewer sent me one chapter. It's 102 manuscript of his translation. It's so surprising. That reviewer is Stefan Lovitz. But anyway, independent of the Chenzo, Bradley Efron also think about something, the structure of poems, statistical inference, and he showed that the curvature plays a very important role in asymptotic statistics. Okay? And he said that he read the also handwritten manuscript of Fisher, unpublished. Fisher did a lot of calculation. What Fisher was calculating, that was curvature in the term of geometry. And also David, A.B. David, he did give very nice comment, and I was shocked to see this. Okay? But I myself, going back to where I was, also just master graduate student. We had some seminar on statistics, and some professor just mentioned the Kullback divergence. Its local thing is something quadratic form. It can be the Riemannian metric. So I just try to calculate what is the curvature, what is the geodesy. It's a good exercise for students. Okay? I enjoy it. And I found it's the constant negative curvature, Poincaré half. So I got shocked. It's beautiful. Beautiful things should have some practically important meaning, but I couldn't find. Okay? So then the time goes on, 10 or more years. And I worked on neural networks and many other applied mathematics. But I think about the reading Efron paper, again, I think about we should work on this line much more. So, with some work, and maybe our originality with Hiroshi Nagaoka, okay, is something we established competitive duality in the affine connection main world, And also in dually flat case, we can find the Pythagorean theorem or projection theorem, or it's connected with divergence. Okay? And then there are a lot of research joining in this field, and I cannot mention so many. And so Pistone, he's working on the functions. It's very difficult. Okay? But our belief is, if we do something, just neglecting difficulty of infinite dimension, everything looks like okay. Mathematician says no, it's never. Okay? But Pistone is it's okay. The mathematician can do is such a very nice foundation, even in this case. Okay. But it's too difficult to me. And also today I know the Professor Koshul has done a lot of such preparation on the dually flat manifold. Okay, we didn't know, I didn't know, but it's a very brilliant finding that there are a lot of the researchers working on this subject. Maybe there are much more. Okay, my talk today is just talk about divergence. Okay, so we think about manifold. We use local coordinate system. What is divergence? Okay, divergence between 2 points, P and Q, or we can write down in terms of coordinates. Point P coordinate and point Q coordinate. So divergence should be non-negative. Okay? And also it should be 0 if and only if P and Q is equal. Okay? And one more important thing is if we do Taylor expansion of this one, when P and Q is very close, the leading term is quadratic term. So first term varies. So second term is this one, and this should be positive definite. So we just require for the divergence this one. And in general, it's not symmetry. Of course, symmetry is special case. Okay? And you can see the divergence from this one. This looks like a Riemannian local distance. Square of Riemannian local distance, that implies divergence has a dimension of square of distance like quantity. Okay. So no triangular inequality hold, and of course not non-symmetric in general, but Pythagorean theorem, it looks like a mirror. Okay, and a little bit of mathematics. Okay, so what one can get the divergence function, some local selection. As I mentioned, okay, if P and Q is very close, we have this point between Riemannian-like distance. Are there any other such local quantity? One can easily find, and I don't want to go details, okay? But so Riemannian distance is just the Taylor expansion of divergence function taken for the. Okay? But we continue a little more Taylor expansion. Then the third order comes in. And because of P and it's not symmetric, it refers to P and Q, we can obtain something, some tensor from this one. And this is the Professor Shun-Ichi when he was very young. Okay? But anyway, so locally, divergence can be two important tensors. One is the Fisher information in the case of probability distribution, okay? And the Riemannian method. is the third order symmetric tensor. Okay? If the divergence is symmetric one, okay, then this tensor varies. So we think about local structure of the manifold with the divergence function can be characterized by two tensors, G, Riemannian metric, and this cubic tensor. Okay, Lorentz called it skew tensor. I don't like that name. Okay? Skew implies something skew symmetric or that. This is symmetric tensor. So maybe simply cubic tensor is a good name. Okay, so one more thing. There's a lot of textbook on Riemannian geometry. Okay, they say that there's a manifold, and the definition is very difficult because that is how should have house topology and okay. But for those non-mathematicians, we like much more intuitive manifold picture, but it's okay. And also Riemannian manifold, it is has the Riemannian metric tensor. Okay. So it consists of M and D. But what we are talking about is the manifold. It is positive tensor, that is your Riemannian metric, and one more tensor, T, cubic tensor. Then what will happen? Okay, so we need to search for those structures consisting of M, G, T. Okay, and the Hessian manifold is a very special case of it, but very important special case. Okay, Riemannian metric. So the tangent direction along the coordinate line, we say this is tangent vector. And for mathematician, tangent vector definition is very nice. It is something directional derivative, satisfying certain fact, okay? But forget about it. Just tangent, right? And so we have the inner product of those one, and it's, if Riemannian structure is defined, it is Riemannian metric tensor, and it comes from divergence, Taylor expansion, and also Tij, it comes from Taylor expansion of T. What is the role of this T tensor in Riemannian geometry? And so, this IJK is Levi-Civita connection. Okay? I do not go into details of Levi-Civita connection, but those who know Levi-Civita connection know very well. Okay, so Levi-Civita connection, we modify Levi-Civita connection by adding this T, or by subtracting, or by forget about that. Okay, we can put some scale. So then we have two affine connections. Okay. If we do the average, just adding them, this cancels out, and the Levi-Civita connection comes out. So it, given Levi-Civita connection, we split them into two opposite directions. Then we have two affine connections. And by this affine connection, we have, of course, defined covariant derivatives and the parallel transport of a tangent vector. Okay? So, those two connections are dual. What is the meaning of dual? We can express in many ways of dual, but one simple idea is, okay, here is the two vector A and B. Transport A parallel to here, along some curve. And transport B parallel by the other then inner product is kept by this one and this one. Okay? So you may think about the Riemannian connection, Levi-Civita connection. In that case, we have only one Levi-Civita connection, and the inner product is kept by parallel transport. Okay? Okay? In the condition under there is no torsion, we can easily prove. And it's a good exercise for graduate students to prove that. Yeah, but anyway, now we have two affine connection, but it's not arbitrary. It's restricted by Riemannian metric such that this whole. Okay? So this is why we call it dual. And if you write those the vector field expression and the covariant derivative and yes, dual connection is like this one. And if we like coordinate expression, we can write down like this way. So it's a technical thing. And since we have two affine connections, what is the geodesic? Okay? The geodesic line, geodesic is the from here to here, it never changes its direction. That is this is the tangent vector of some curve, and the derivative along its tangent direction should be zero. This implies direction never changes going around. This is the definition of the geodesic. But in our case, we have two affine connections. So if we have 2 points, there are 2 geodesics connecting them. Okay? So think about Euclidean space. What is the straight line? Of course, it is the line, its length is minimized among all curves connecting to points. So minimum distance curve. Okay, this is one property. But the other property, it never changes its direction. Okay. So now we are thinking about Riemannian manifold. What definition we like? Okay. If we like minimum distance property, we have Levi-Civita connection. Okay. And also it's a student exercise. So from variational equation to the Levi-Civita connection. But if we say we don't care about minimum distance, but the straightness is very important, then we have the extension of straight line, but not shortest. However, this should not be arbitrary. We have 2 geodesics, and by 2 dually affine connection. So in Euclidean space, these 2 concepts just coincide. In a dual space, they split. Okay? But still, they have its own meaning. So now we come to the dually flat structure. The manifold with dual connection, of course, it's not necessarily flat. What is a flat? Flat implies if we transport A parallel along this loop, okay? So vector A, they do the round the world parallel transit. Okay, go to Japan, Paris, America, back to Japan. Then the tangent vector change its direction if there is a curvature. Okay, if it vanishes, there's no curvature. So parallel transport is always the same. Okay? And in this case, if dually flat, if curvature, Riemann-Christoffel curvature vanishes, it implies automatically dual Riemann-Christoffel curvature vanishes. This is simply proved because A and B at this point, okay, we parallelly transport A around the world too. And also this guy, also the same around the world too. Okay? And if this is equal, and if R is 0, pi A is A. And pi A is A implies this and this is equal. That implies pi star B is B. Very simple proof. Okay? I like simple proof. Complicated proof. Usually it doesn't. Okay, so now we go to the dually flat manifold or Hessian manifold. Okay? That is manifold with two dual connections and also curvature, two curvature spaces. In such case, we can actually prove that there is an affine coordinate system such that affine connection is zero everywhere. Okay? And also, because of R star is zero, there is another coordinate system. It's a dual affine coordinate system, and this should be manifold dually flat. One thing is we have two affine coordinate systems such that affine connection varies. Okay? And in this case also we can prove there exists convex function for this one, psi, for corresponding theta, another convex function, and such that theta and eta is connected by Legendre transformation. This is very interesting structure, and we write down the dual coordinate or eta coordinate is gradient of psi function, where di implies dt theta I, and the theta I is the gradient of dual convex function. Okay, so because the Legendre transformation is satisfied if the same point, its theta coordinate theta, and its dual affine coordinate theta, this is Legendre transformation. And the Riemannian metric is just Hessian, so we call this one Hessian manifold, and we can very easily prove this and this is mutually inverse matrix. And what is the T? In this dually flat case, it's just the triple differentiation of this guy and also this guy. Of course, the upper contravariant index and covariant index is connected by GIG. And moreover,